Hi, this is Chris, and in this video in our series on torque, we are going to take a look at a scenario where you have a fixed point, but it's not on the end of your lever arm in this case, but it's going to be somewhere in the middle. And oftentimes you'll see this sort of seesaw type setup, and depending on the question, but sometimes maybe they'll ask you where you would have to place a particular mass in order to have it balanced, or sometimes they'll ask you just with an existing scenario, which way is it going to go? Is the seesaw going to lower on the left side there, or is it going to lower on the right side, or what's going to happen? So these scenarios are really going to come back to our basic torque equation. Now we see up here, which is tau equals RF sine theta. And so let's see if we were to calculate each torque individually. And we mentioned it in the first video, but here, if torque goes in this direction, which would be, if you think of it like a circle, would be counterclockwise. Counterclockwise direction is considered positive. And if torque were to go in this direction, clockwise direction, that would be considered negative. So we assign a direction, because remember, force is a vector, and anytime you're talking about anything with force, if you're talking about vector components, force, velocity, direction matters. And negative, all that a negative means when you're talking about a vector is a negative just indicates direction. So a negative means something in the opposite direction. So here, for example, if we're given values, and let's write in some values here so we can do this as a numerical calculation. So let's say for our purposes, we'll do mass 1 equals 10 kilograms. And we'll do R1 equals 6 meters. And then for mass 2, we'll do, let's say, 20 kilograms. And we'll do R2 equals 4 meters. All right, so let's see how that works if we were to apply this to our torque equation for these two scenarios. We're going to see which direction our seesaw would tip for this. So this is going to be our first torque question where we have a fulcrum or a fixed point somewhere in between masses, and we want to figure out how that's going to relate to torque. So to plug in our values here, so for torque 1, we would have 6 for R. Our force, so our force here is going to be purely due to gravitational force. So our force is acting straight down, right, as a result of that mass. The torque is going to have that rotational component, but the force on mass 1 would be straight down. That's our gravitational component, and gravity is mg. So this would be, for mass 1, you would have 10 kilograms times your value of g, which would be 9.8, or sometimes 9.81, or sometimes you might even be allowed to round it to 10. Depends on, how specific your teacher wants you to get with those corresponding values, or what answer choices you're looking at. For example, if it's on a standardized test or on a multiple choice test. So here you'd have 6 times 10 times 9.8, and then we have to figure out our angle. Well, here, if we were to look at our force due to gravity, which acts straight down on that mass, and here if we look at our axis of rotation, which is horizontal, we see that those are at a 90-degree angle. Those are perpendicular to one another. So we're plugging in a value of 90 for sine. And we can write it in here. I wrote this a little big, so I'm going to maybe make it a touch smaller, but here you're going to have sine 90, and since sine 90 is 1, we don't actually have to worry about that part of the calculation. Here you'll have your torque, which is 6 times 10 is 60 times 9.8, so that would be 588. And this is going to be in the positive direction, so we can think of this as a positive 588, because just like with any free body diagram on an object, you want to look at your sum of your forces in terms of net force. In this case, you're going to do the same thing with torque. You're going to look at how these sum together. One will be positive, one will be negative. So now let's take a look at our second torque here, and we're going to plug in 4 for R. We're going to plug in 20 for our mass, 9.8 for our acceleration due to gravity, and the sine of 90 degrees, because this one is also perpendicular for the same reason as the first. And if we do the math on this, then we're going to get 4 times 20, which is 80, times 9.8, which is 784 times 1. So we'll have a value of 784. And this will be in the negative direction, right? Because this one, as we set up here, is going clockwise, which conventionally we use negative for clockwise torque and we use positive for counterclockwise torque. Now, if we were to sum those values together, which basically means that you're adding a positive 588 and a negative 784, that comes out to the sum of our torques for our net torque. That would be torque 1 and torque 2 would be a total of negative 196, which means that that is your resulting torque. So it's going to be a torque of 196 in that clockwise direction. And that's because our mass was greater, our radius was smaller, but if we look here, that total torque value is going to be greater in this clockwise direction. So that's the direction that our seesaw would tip. Our seesaw, in this case, after we allow those masses on the seesaw, we're going to have mass 1 up in the air and mass 2 on the ground in that scenario. Now coming up, we're going to take a look at a similar situation but with different missing values. So stay tuned and we'll check that out in a minute.